Oh, and how do I? What is How do I go to that live page, bro, where you see all of that stuff? Oh my god. Why do I not remember this?
Generative pre-trained transformer. So that first word is straightforward enough. These are bots that generate new text. Pre-trained refers to how the model went through a process of learning from a massive amount of data, and the prefix insinuates that there's more room to fine-tune it on specific tasks with additional training. But the last word, that's the real key piece. A transformer is a specific kind of neural network, a machine learning model, and it's the core invention underlying the current boom in AI. What I want to do with this video and the following chapters is go through a visually driven explanation for what actually happens inside a transformer. We're going to follow the data that flows through it and go step by step. There are many different kinds of models that you can build using transformers. Some models take in audio and produce a transcript.
This sentence comes from a model going the other way around, producing synthetic speech just from text.
All those tools that took the world by storm in 2022, like Dolly and Midjourney, that take in a text description and produce an image, are based on transformers. Even if I can't quite get it to understand what a pie creature is supposed to be, I'm still blown away that this kind of thing is even remotely possible. And the original transformer, introduced in 2017 by Google, was invented for the specific use case of translating text from one language into another. Google was possible. And the original transformer, introduced in 2017 by Google, was invented for the specific use case of translating text from one language into another. But the variant that you and I will focus on, which is the type that underlies tools like ChatGPT, will be a model that's trained to take in a piece of text, maybe even with some surrounding images or sound accompanying it, and produce a prediction for what comes next in the passage. That prediction takes the form of a probability distribution over many different chunks of text that might follow. At first glance, you might think that predicting the next word feels like a very different goal from generating new text. But once you have a prediction model like this, a simple thing you could try to make it generate a longer piece of text is to give it an initial snippet to work with, have it take a random sample from the distribution it just generated, append that sample to the text, and then run the whole process again to make a new prediction based on all the new text, including what it just added. I don't know about you, but it really doesn't feel like this should actually work. In this animation, for example, I'm running GPT-2 on my laptop and having it repeatedly predict and sample the next chunk of text to generate a story based on the seed text. And the story just doesn't actually really make that much sense. But if I swap it out for API calls to GPT-3 instead, which is the same basic model, just much bigger, suddenly, almost magically, we do get a sensible story, one that even seems to infer that a pie creature would live in a land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT or any of these other large language models and you see them producing one word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word that it chooses. Let's kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high-dimensional space, words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated. And again, whenever I use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron or maybe a feed-forward layer. And here, the vectors don't talk to each other. They all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how the step is a little bit like asking a long list of questions about each vector, and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications, and our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multi-layer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text, that might come next. And like I said, once you have a tool that predicts what comes next given a snippet of text, you can feed it a little bit of seed text and have it repeatedly play this game of predicting what comes next, sampling from the distribution, appending it, and then repeating over and over. Some of you in the know may remember how, long before ChatGPT came into the scene, this is what early demos of GPT-3 looked like. You would have it autocomplete stories and essays based on an initial snippet. To make a tool like this into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant, what you would call the system prompt, and then you would use the user's initial question or prompt as the first bit of dialogue, and then you have it start predicting what such a helpful AI assistant would say in response. There is more to say about an added step of training that's required to make this work well, but at a high level, this is the general idea. In this chapter, you and I are going to expand on the details of what happens at the very beginning of the network, at the very end of the network, and I also want to spend a lot of time reviewing some important bits of background knowledge, things that would have been second nature to any machine learning engineer by the time transformers came around. If you're comfortable with that background knowledge and a little impatient, you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks, generally considered the heart of the transformer. After that, I want to talk more about these multi-layer perceptron blocks, how training works, and a number of other details that will have been skipped up to that point. For broader context, these videos are additions to a mini-series about deep learning, and it's okay if you haven't watched the previous ones. I think you can do it out of order. But before diving into transformers specifically, I do think it's worth making sure that we're on the same page about the basic premise and structure of deep learning. At the risk of stating the obvious, this is one approach to machine learning, which describes any model where you're using data to somehow determine how a model behaves. What I mean by that is, let's say you want a function that takes in an image and it produces a label describing it, or our example of predicting the next word given a passage of text, or any other task that seems to require some element of intuition and pattern recognition. We almost take this for granted these days, but the idea with machine learning is that rather than trying to explicitly define a procedure for how to do that task in code, which is what people would have done in the earliest days of AI, instead, you set up a very flexible structure with tunable parameters, like a bunch of knobs and dials, and then, somehow, you use many examples of what the output should look like for a given input to tweak and tune the values of those parameters to mimic this behavior. For example, maybe the simplest form of machine learning is linear regression, where your inputs and your outputs are each single numbers, something like the square footage of a house and its price. And what you want is to find a line of best fit through this data, to predict future house prices. That line is described by two continuous parameters, say the slope and the y-intercept, and the goal of linear regression is to determine those parameters to closely match the data. Needless to say, deep learning models get much more complicated. GPT-3, for example, has not 2, but 175 billion parameters. But here's the thing. It's not a given that you can create some giant model with a huge number of parameters without it either grossly overfitting the training data or being completely intractable to train. Deep learning describes a class of models that, in the last couple decades, have proven to scale remarkably well. What unifies them is that they all use the same training algorithm. It's called backpropagation. We talked about it in previous chapters. And the context that I want you to have as we go in is that in order for this training algorithm to work well at scale, these models have to follow a certain specific format. And if you know this format going in, it helps to explain many of the choices for how a transformer processes language, which otherwise run the risk of feeling kind of arbitrary. First, whatever kind of model you're making, the input has to be formatted as an array of real numbers. This could simply mean a list of numbers, it could be a two-dimensional array, or very often you deal with higher dimensional arrays, where the general term used is tensor. You often think of that input data as being progressively transformed into many distinct layers, where again, each layer is always structured as some kind of array of real numbers, until you get to a final layer which you consider the output. For example, the final layer in our text processing model is a list of numbers representing the probability distribution for all possible next tokens. In deep learning, these model parameters are almost always referred to as weights, and this is because a key feature of these models is that the only way these parameters interact with the data being processed is through weighted sums. You also sprinkle some nonlinear functions throughout, but they won't depend on parameters. Typically, though, instead of seeing the weighted sums all naked and written out explicitly like this, you'll instead find them packaged together as various components in a matrix vector product. It amounts to saying the same thing. If you think back to how matrix vector multiplication works, each component in the output looks like a weighted sum. It's just often conceptually cleaner for you and me to think about matrices that are filled with tunable parameters that transform vectors that are drawn from the data being processed. For example, those 175 billion weights in GPT-3 are organized into just under 28,000 distinct matrices. Those matrices in turn fall into 8 different categories, and what you and I are going to do is step through each one of those categories to understand what that type does. As we go through, I think it's kind of fun to reference the specific numbers from GPT-3 to count up exactly where those 175 billion come from. Even if nowadays there are bigger and better models, this one has a certain charm as the first large language model to really capture the world's attention outside of ML communities. Also, practically speaking, companies tend to keep much tighter lips around the specific numbers for more modern networks. I just want to set the scene going in, that as you peek under the hood to see what happens inside a tool like ChatGPT, almost all of the actual computation looks like matrix vector multiplication. There's a little bit of a risk getting lost in the sea of billions of numbers, but you should draw a very sharp distinction in your mind between the weights of the model, which I'll always color in blue or red, and the data being processed, which I'll always color in gray. The weights are the actual brains. They are the things learned during training, and they determine how it behaves. The data being processed simply encodes whatever specific input is fed into the model for a given run, like an example snippet of text. With all of that as foundation, let's dig into the first step of this text processing example, which is to break up the input into little chunks and turn those chunks into vectors. I mentioned how those chunks are called tokens, which might be pieces of words or punctuation, but every now and then in this chapter, and especially in the next one, I'd like to just pretend that it's broken more cleanly into words. Because we humans think in words, this will just make it much easier to reference little examples and clarify each step. The model has a predefined vocabulary, some list of all possible words, say 50,000 of them, and the first matrix that we'll encounter, known as the embedding matrix, has a single column for each one of these words. These columns are what determines what vector each word turns into in that first step. We label it WE, and like all the matrices we see, its values begin random, but they're going to be learned based on data. Turning words into vectors was common practice in machine learning long before transformers, but it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment to get familiar with it. We often call this embedding a word, which invites you to think of these vectors very geometrically, as points in some high-dimensional space. Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much higher dimensional. In GPT-3, they have 12,288 dimensions, and as you'll see, it matters to work in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice, for the sake of animating word embeddings that a simple model is giving me, I'm going to do an analogous thing by choosing a 3-dimensional slice through this very high-dimensional space and projecting the word vectors down onto that and displaying the results. The big idea here is that as a model tweaks and tunes its weights to determine how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea that directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch, you could find it by taking king, adding this woman minus man direction, and searching on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea that directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch, you could find it by taking king, adding this woman minus man direction, and searching for the embeddings closest to that point. At least, kind of. Despite this being a classic example, for the model I'm playing with, the true embedding of queen is actually a little farther off than this would suggest, presumably because the way that queen is used in training data is not merely a feminine version of king. When I played around, family relations seemed to illustrate the idea much better. The point is, it looks like during training the model found it advantageous to choose embeddings such that one direction in this space encodes gender information. Another example is that if you take the embedding of Italy and you subtract the embedding of Germany, and then you add that to the embedding of Hitler, you get something very close to the embedding of Mussolini. It's as if the model learned to associate some directions with Italianness and others with World War II Axis leaders. Maybe my favorite example in this vein is how in some models, if you take the difference between Germany and Japan and you add it to sushi, you end up very close to bratwurst. Also, in playing this game of finding nearest neighbors, I was very pleased.
Fuck is breakfast? Sausage. Damn. Look. No comments. No one watching also. Nice.
To see how close cat was to both beast and monster. One bit of mathematical intuition that's helpful to have in mind, especially for the next chapter, is how the dot product of two vectors can be thought of as a way to measure how well they align. Computationally, dot products involve multiplying all the corresponding components and then adding the results, which is good since so much of our computation has to look like weighted sums. Geometrically, the dot product is positive when vectors point in similar directions, it's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example, let's say you were playing with this model and you hypothesize that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values, so it's as if we can quantitatively measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257, and again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we should count up to 175 billion. In the case of transformers, you really want to think of the vectors in this embedding space as not merely representing individual words. For one thing, they also encode information about the position of that word, which we'll talk about later. But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example, might progressively get tugged and pulled by various blocks in this network, so that by the end it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland, and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continued too long. We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words like Harry Potter, and immediately preceding we see least favorite teacher, and also if you give me some leeway by letting me pretend that tokens simply look like full words, then a well-trained network that had built up knowledge of Harry Potter would presumably assign a high number to the word Snape. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that in the training process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over a billion. A small, but not wholly insignificant fraction of the 175 billion that we'll end up with in total. As the very last mini-lesson for this chapter, I want to talk more about the softmax function, since it makes another appearance for us once we dive into the attention blocks. The idea is that if you want a sequence of numbers to act as a probability distribution, say a distribution over all possible next words, then each value has to be between 0 and 1, and you also need all of them to add up to 1. However, if you're playing the deep learning game, where everything you do looks like matrix vector multiplication, the outputs that you get by default don't abide by this at all. The values are often negative or much bigger than 1, and they almost certainly don't add up to 1. Softmax is the standard way to turn an arbitrary list of numbers into a valid distribution in such a way that the largest values end up closest to 1, and the smaller values end up very close to 0. That's all you really need to know. But if you're curious, the way that it works is to first raise e to the power of each of the numbers, which means you now have a list of positive values, and then you can take the sum of all those positive values and divide each term by that sum, which normalizes it into a list that adds up to 1. You'll notice that if one of the numbers in the input is meaningfully bigger than the rest, then in the output, the corresponding term dominates the distribution. So if you were sampling from it, you'd almost certainly just be picking the maximizing input. But it's softer than just picking the max, in the sense that when other values are similarly large, they also get meaningful weight in the distribution, and everything changes continuously as you continuously vary the inputs. In some situations, like when ChatGPT is using this distribution to create a next word, there's room for a little bit of extra fun by adding a little extra spice into this function with a constant t thrown into the denominator of those exponents. We call it the temperature since it vaguely resembles the role of temperature in certain thermodynamics equations, and the effect is that when t is larger, you give more weight to the lower values, meaning the distribution is a little bit more uniform. And if t is smaller, then the bigger values will dominate more aggressively. Where in the extreme, setting t equal to 0 means all of the weight goes to that maximum value. For example, I'll have GPT-3 generate a story with the seed text, "Once upon a time there was a," but I'm going to use different temperatures in each case. Temperature 0 means that it always goes with the most predictable word. And what you get ends up being kind of a trite derivative of Goldilocks. A higher temperature gives it a chance to choose less likely words, but it comes with a risk. In this case, the story starts out a bit more originally, about a young web artist from South Korea, but it quickly degenerates into nonsense. Technically speaking, the API doesn't actually let you pick a temperature bigger than 2. There is no mathematical reason for this. It's just an arbitrary constraint imposed, I suppose, to keep their tool from being seen generating things that are too nonsensical. So if you're curious, the way this animation is actually working is I'm taking the 20 most probable next tokens that GPT-3 generates, which seems to be the maximum they'll give me, and then I tweak the probabilities based on an exponent of 1/5. As another bit of jargon, in the same way that you might call the components of the output of this function probabilities, people often refer to the inputs as logits, or some people say logits, some people say logits. I'm going to say logits. So for instance, when you feed in some text, you have all these word embeddings flow through the network, and you do this final multiplication with the unembedding matrix. Machine learning people would refer to the components in that raw, unnormalized output as the logits for the next word prediction. A lot of the goal with this chapter was to lay the foundations for understanding the attention mechanism, Karate Kid wax on, wax off style. You see, if you have a strong intuition for word embeddings, for softmax, for how dot products measure similarity, and also the underlying premise that most of the calculations have to look like matrix multiplication with matrices full of tunable parameters, then understanding the attention mechanism, this cornerstone piece in the whole modern boom in AI, should be relatively smooth. For that, come join me in the next chapter. As I'm publishing this, a draft of that next chapter is available for review by Patreon supporters. In the last chapter, you and I... The initials...
What do you mean by reverse engineering such models? Why do I feel like we just don't know how this stuff works, and like we've just built it and it just exists now? All 2021. So. कितनी बारी की चीज़ मेंशन किया about this? What the fuck? This is a very dramatic situation. So they're basically using a very basic transformer, as they've been saying, starting say. But damn, like they're basically stripping it off every single thing, like ignore layer normalization, ignore biases and shit like that. But damn, okay. High level architecture. Okay, we'll do this some other time. Yeah, it's very weird how everyone's like they might be doing like what the fuck. Um, you're probably able to hear a train. I know no one's watching, but that's a train. I live near a railway track, that's why. These are free resources. I don't get it. What? Is it free or is it not free? Who is Dave? Give me this bullshit. Is that a platform somewhere? But no, GPT learning hub. The domain is different. This guy buy it and it's just happened.
I don't.
This is nice.
GPT stand for.
Wait 1 sec.
I don't even know what it would mean to learn backpropagation before gradient descent. I think it's really fair to describe some of what's coming out of just this like next token addition as reasoning, as a kind of chain of thought. Seems pretty silly to be shaking in your boots as a software engineer.
Yeah, I've been a huge fan of your videos since I was taking like high school calculus and
Or In the last chapter, you and I started to step through the internal workings of a transformer. This is one of the key pieces of technology inside large language models, and a lot of other tools in the modern wave of AI. It first hit the scene in a now famous 2017 paper called Attention is All You Need, and in this chapter, you and I will dig into what this attention mechanism is, visualizing how it processes data. As a quick recap, here's the important context I want you to have in mind. The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces that we call tokens, and these are very often words or pieces of words. But just to make the examples in this video easier for you and me to think about, let's simplify by pretending that tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional vector, what we call its embedding. Now, the most important idea I want you to have in mind is how directions in this high-dimensional space of all possible embeddings can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is to progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much richer contextual meaning. I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing, so don't worry if it takes some time for things to sink in. I think that before we dive into the computational details and all the matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want attention to enable. Consider the phrases American shrew mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all 3 of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions, as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non-specific direction in the space, associated with lots of other large, tall nouns. If this word was immediately preceded by Eiffel, you could imagine wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, maybe correlated with vectors associated with Paris and France and things made of steel. If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things. More generally than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model's going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word was, will have to have been updated by all of the attention blocks to represent much, much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. To step through the computations, though, let's take a much simpler example. Imagine that the input includes the phrase, "A fluffy blue creature roamed the verdant forest." And for the moment, suppose that the only type of update that we care about is having the adjectives adjust the meanings of their corresponding nouns. What I'm about to describe is what we would call a single head of attention, and later we will see how the attention block consists of many different heads run in parallel. Again, the initial embedding for each word is some high-dimensional vector that only encodes the meaning of that particular word with no context. Actually, that's not quite true. They also encode the position of the word. There's a lot more to say about the specific way that positions are encoded, but right now, all you need to know is that the entries of this vector are enough to tell you both what the word is and where it exists in the context. Let's go ahead and denote these embeddings with the letter E. The goal is to have a series of computations produce a new refined set of embeddings, where, for example, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. And playing the deep learning game, we want most of the computations involved to look like matrix vector products, where the matrices are full of tunable weights, things that the model will learn based on data. To be clear, I'm making up this example of adjectives updating nouns just to illustrate the type of behavior that you could imagine an attention head doing. As with so much deep learning, the true behavior is much harder to parse, because it's based on tweaking and tuning a huge number of parameters to minimize some cost function. It's just that as we step through all of the different matrices filled with parameters that are involved in this process, I think it's really helpful to have an imagined example of something that it could be doing to help keep it all more concrete. For the first step of this process, you might imagine each noun, like creature, asking the question, "Hey, are there any adjectives sitting in front of me?" And for the words fluffy and blue to each be able to answer, "Yeah, I'm an adjective and I'm in that position." That question is somehow encoded as yet another vector, another list of numbers, which we call the query for this word. This query vector, though, has a much smaller dimension than the embedding vector, say 128. Computing this query looks like taking a certain matrix, which I'll label WQ, and multiplying it by the embedding. Compressing things a bit, let's write that query vector as Q, and then anytime you see me put a matrix next to an arrow like this one, it's meant to represent that multiplying this matrix by the vector at the arrow's start gives you the vector at the arrow's end. In this case, you multiply this matrix by all of the embeddings in the context, producing one query vector for each token. The entries of this matrix are parameters of the model, which means the true behavior is learned from data, and in practice, what this matrix does in a particular attention head is challenging to parse. But for our sake, imagining an example that we might hope that it would learn, we'll suppose that this query matrix maps the embeddings of nouns to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it simultaneously tries to accomplish some other goal with those. Right now, we're laser focused on the nouns. At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces a second sequence of vectors that we call the keys. Conceptually, you want to think of the keys as potentially answering the queries. This key matrix is also full of tunable parameters, and just like the query matrix, it maps the embedding vectors to that same smaller dimensional space. You think of the keys as matching the queries whenever they closely align with each other. In our example, you would imagine that the key matrix maps the adjectives, like fluffy and blue, to vectors that are closely aligned with the query produced by the word creature. To measure how well each key matches each query, you compute a dot product between each possible key query pair. I like to visualize a grid full of a bunch of dots, where the bigger dots correspond to the larger dot products, the places where the keys and queries align. For our adjective-noun example, that would look a little more like this, where if the keys produced by fluffy and blue really do align closely with the query produced by creature, then the dot products in these two spots would be some large positive numbers. In the lingo, machine learning people would say that this means the embeddings of fluffy and blue attend to the embedding of creature. By contrast to the dot product between the key for some other word, like the, and the query for creature, would be some small or negative value that reflects that these are unrelated to each other. So we have this grid of values that can be any real number from -infinity to infinity, giving us a score for how relevant each word is to updating the meaning of every other word. The way we're about to use these scores is to take a certain weighted sum, giving us a...
Shouldn't this diagonal be 0? Because like creature को क्या ही update करेगा bro? Look, A and A, okay, it's close to 0, to be fair, compared to like 93, 4.7, nothing. 7, Understandable. Yeah, it's close to 0 indeed. Perception analysis. Okay.
Score for how relevant each word is to updating the meaning of every other word. The way we're about to use these scores is to take a certain weighted sum along each column, weighted by the relevance. So instead of having values range from -infinity to infinity, what we want is for the numbers in these columns to be between 0 and 1, and for each column to add up to 1, as if they were a probability distribution. If you're coming in from the last chapter, you know...
I think I studied softmax in college. I don't know why I was so surprised at softmax. What the fuck?
What we need to do then, we compute a softmax along each one of these columns to normalize the values. In our picture, after you apply softmax to all of the columns, we'll fill in the grid with these normalized values. At this point, you're safe to think about each column as giving weights according to how relevant the word on the left is to the corresponding value at the top. We call this grid an attention pattern. Now, if you look at the original Transformer paper, there's a really compact way that they write this all down. Here, the variables q and k represent the full arrays of query and key vectors respectively, those little vectors you get by multiplying the embeddings by the query and the key matrices. This expression up in the numerator is a really compact way to represent the grid of all possible dot products between pairs of keys and queries. A small technical detail that I didn't mention is that for numerical stability, it happens to be helpful to divide all of these values by the square root of the dimension in that key query space.
Why?
Then this soft
You do so many random.
the square
Why
root of
Why did he choose root of dimensions of k? Like, so why didn't you divide it by like 2 or something? I don't know. क्या ये?
the dimension in that key query space. Then this softmax that's wrapped around the full expression is meant to be understood to apply column by column. As to that v term, we'll talk about it in just a second. Before that, there's one other technical detail that so far I've skipped. During the training process, when you run this model on a given text example, and all of the weights are slightly adjusted and tuned to either reward or punish it based on how high a probability it assigns to the true next word in the passage, it turns out to make the whole training process a lot more efficient if you simultaneously have it predict every possible next token following each initial subsequence of tokens in this passage. For example, with the phrase that we've been focusing on, it might also be predicting what words follow creature and what words follow the. This is really nice because it means what would otherwise be a single training example effectively acts as many. For the purposes of our attention pattern, it means that you never want to allow later words to influence earlier words, since otherwise they could kind of give away the answer for what comes next. What this means is that we want all of these spots here, the ones representing later tokens influencing earlier ones.
I feel like the answer to that question lies somewhere in stats and linear algebra. That's another trait. But maybe somewhere in maths. Should I be choosing math or what? Oh my god.
To somehow be forced to be 0. The simplest thing you might think to do is to set them equal to 0, but if you did that, the columns wouldn't add up to 1 anymore. They wouldn't be normalized. So instead, a common way to do this is that before applying softmax, you set all of those entries to be negative infinity. If you do that, then after applying softmax, all of those get turned into 0, but the columns stay normalized. This process is called masking. There are versions of attention where you don't apply it, but in our GPT example, even though this is more relevant during the training phase than it would be, say, running it as a chatbot or something like that, you do always apply this masking to prevent later tokens from influencing earlier ones. Another fact that's worth reflecting on about this attention pattern.
But later tokens should influence earlier ones, no? No, later tokens should. I can't think of an example जहाँ पे later words that come later in the sentence influence the words that come before. Maybe pronouns like gender wise. Like you would only say he if it was a guy later in the sentence. You wouldn't say, you wouldn't mention that, you wouldn't change the gender based on what came before. That can be one thing.
Influencing earlier ones. Another fact that's worth reflecting on about this attention pattern is how its size is equal to the square of the context size. So this is why
What?
context size can be a really huge bottleneck for large language models, and scaling it up is non-trivial. As you might imagine, motivated by a desire for bigger and bigger context windows, recent years have seen some variations to the attention mechanism aimed at making context more scalable. But right here, you and I are staying focused on the basics.
What the fuck?
Okay, great. Computing this pattern lets the model deduce which words are relevant to which other words. Now, you need to actually update the embeddings, allowing words to pass information to whichever other words they're relevant to. For example, you want the embedding of fluffy to somehow cause a change to creature that moves it to a different part of this 12,000 dimensional embedding space that more specifically encodes a fluffy creature. What I'm going to do here is first show you the most straightforward way that you could do this, though there's a slight way that this gets modified in the context of multi-headed attention. This most straightforward way would be to use a third matrix, what we call the value matrix, which you multiply by the embedding of that first word, for example, fluffy. The result of this is what you would call a value vector, and this is something that you add to the embedding of the second word, in this case something you add to the embedding of creature. So this value vector lives in the same very high dimensional space as the embeddings. When you multiply this value matrix by the embedding of a word, you might think of it as saying, if this word is relevant to adjusting the meaning of something else, what exactly should be added to the embedding of that something else in order to reflect this? Looking back in our diagram, let's set aside all of the keys and the queries, since after you compute the attention pattern, you're done with those. Then you're going to take this value matrix and multiply it by every one of those embeddings to produce a sequence of value vectors. You might think of these value vectors as being kind of associated with the corresponding keys. For each column in this diagram, you multiply each of the value vectors by the corresponding weight in that column. For example, here, under the embedding of creature, you would be adding large proportions of the value vectors for fluffy and blue, while all of the other value vectors get zeroed out, or at least nearly zeroed out. And then finally, the way to actually update the embedding associated with this column, previously encoding some context-free meaning of creature, you add together all of these rescaled values in the column, producing a change that you want to add that I'll label delta E, and then you add that to the original embedding. Hopefully, what results is a more refined vector encoding the more contextually rich meaning, like that of a fluffy blue creature. And of course, you don't just do this to one embedding, you apply the same weighted sum across all of the columns in this picture, producing a sequence of changes. Adding all of those changes to the corresponding embeddings produces a full sequence of more refined embeddings popping out of the attention block. Zooming out, this whole process is what you would describe as a single head of attention. As I've described things so far, this process is parameterized by three distinct matrices, all filled with tunable parameters: the key, the query, and the value. I want to take a moment to continue what we started in the last chapter with the scorekeeping where we count up the total number of model parameters using the numbers from GPT-3. These key and query matrices each have 12,288 columns, matching the embedding dimension, and 128 rows, matching the dimension of that smaller key query space. This gives us an additional 1.5 million or so parameters for each one. If you look at that value matrix by contrast, the way I've described things so far would suggest that it's a square matrix that has 12,288 columns and 12,288 rows, since both its inputs and its outputs live in this very large embedding space. If true, that would mean about 150 million added parameters. And to be clear, you could do that. You could devote orders of magnitude more parameters to the value map than to the key and query. But in practice, it is much more efficient if instead you make it so that the number of parameters devoted to this value map is the same as the number devoted to the key and the query. This is especially relevant in the setting of running multiple attention heads in parallel. The way this looks is that the value map is factored as a product of two smaller matrices. Conceptually, I would still encourage you to think about the overall linear map, one with inputs and outputs both in this larger embedding space, for example, taking the embedding of blue to this blueness direction that you would add to nouns. It's just that it's broken up into two separate steps. The first matrix on the right here has a smaller number of rows, typically the same size as the key query space. What this means is you can think of it as mapping the large embedding vectors down to a much smaller space. This is not the conventional naming, but I'm going to call this the value down matrix. The second matrix maps from this smaller space back up to the embedding space, producing the vectors that you use to make the actual updates. I'm going to call this one the value up matrix, which again is not conventional. The way that you would see this written in most papers looks a little different. I'll talk about it in a minute. In my opinion, it tends to make things a little more conceptually confusing. To throw in linear algebra jargon here, what we're basically doing is constraining the overall value map to be a low-rank transformation. Turning back to the parameter count, all four of these matrices have the same size, and adding them all up, we get about 6.3 million parameters for one attention head. As a quick side note, to be a little more accurate, everything described so far is what people would call a self-attention head, to distinguish it from a variation that comes up in other models that's called cross-attention. This isn't relevant to our GPT example, but if you're curious, cross-attention involves models that process two distinct types of data, like text in one language and text in another language that's part of an ongoing generation of a translation, or maybe audio input of speech and an ongoing transcription. A cross-attention head looks almost identical. The only difference is that the key and query maps act on different data sets. In a model doing translation, for example, the keys might come from one language, while the queries come from another, and the attention pattern could describe which words from one language correspond to which words in another. And in this setting, there would typically be no masking, since there's not really any notion of later tokens affecting earlier ones. Staying focused on self-attention, though, if you understood everything so far, and if you were to stop here, you would come away with the essence of what attention really is. All that's really left to us is to lay out the sense in which you do this many, many different times. In our central example, we focused on adjectives updating nouns, but of course, there are lots of different ways that context can influence the meaning of a word. If the words, "they crashed thee," preceded the word car, it has implications for the shape and the structure of that car. And a lot of associations might be less grammatical. If the word wizard is anywhere in the same passage as Harry, it suggests that this might be referring to Harry Potter. Whereas if instead the words Queen, Sussex, and William were in that passage, then perhaps the embedding of Harry should instead be updated to refer to the prince. For every different type of contextual updating that you might imagine, the parameters of these key and query matrices would be different to capture the different attention patterns, and the parameters of our value map would be different based on what should be added to the embeddings. And again, in practice, the true behavior of these maps is much more difficult to interpret, where the weights are set to do whatever the model needs them to do to best accomplish its goal of predicting the next token. As I said before, everything we described is a single head of attention, and a full attention block inside a transformer consists of what's called multi-headed attention, where you run a lot of these operations in parallel, each with its own distinct key, query, and value maps. GPT-3, for example, uses 96 attention heads inside each block. Considering that each one is already a bit confusing, it's certainly a lot to hold in your head. Just to spell it all out very explicitly, this means you have 96 distinct key and query matrices, producing 96 distinct attention patterns. Then each head has its own distinct value matrices, used to produce 96 sequences of value vectors. These are all added together, using the corresponding attention patterns as weights. What this means is that for each position in the context, each token, every one of these heads produces a proposed change to be added to the embedding in that position. So what you do is you sum together all of those proposed changes, one for each head, and you add the result to the original embedding of that position. This entire sum here would be one slice of what's outputted from this multi-headed attention block, a single one of those refined embeddings that pops out the other end of it. Again, this is a lot to think about, so don't worry at all if it takes some time to sink in. The overall idea is that by running many distinct heads in parallel, you're giving the model the capacity to learn many distinct ways that context changes meaning. Pulling up our running tally for parameter count, with 96 heads, each including its own variation of these four matrices, each block of multi-headed attention ends up with around 600 million parameters. There's one added, slightly annoying thing that I should really mention for any of you who go on to read more about transformers. You remember how I said that the value map is factored out into these two distinct matrices, which I labeled as the value down and the value up matrices. The way that I framed things would suggest that you see this pair of matrices inside each attention head. And you could absolutely implement it this way. That would be a valid design. But the way that you see this written in papers and the way that it's implemented in practice looks a little different. All of these value up matrices for each head appear stapled together in one giant matrix that we call the output matrix, associated with the entire multi-headed attention block. And when you see people refer to the value matrix for a given attention head, they're typically only referring to this first step, the one that I was labeling as the value down projection into the smaller space. For the curious among you, I've left an on-screen note about it. It's one of those details that runs the
Why 96? Oh, because that leaves 96 attention heads.
The risk of distracting from the main conceptual points, but I do want to call it out just so that you know if you read about this in other sources. Setting aside all the technical nuances, in the preview from the last chapter, we saw how data flowing through a transformer doesn't just flow through a single attention block. For one thing, it also goes through these other operations called multi-layer perceptrons. We'll talk more about those in the next chapter. And then it repeatedly goes through many copies of both of these operations. What this means is that after a given word imbibes some of its context, there are many more chances for this more nuanced embedding to be influenced by its more nuanced surroundings. The further down the network you go, with each embedding taking in more and more meaning from all the other embeddings, which themselves are getting more and more nuanced, the hope is that there's the capacity to encode higher level and more abstract ideas about a given input beyond just descriptors and grammatical structure. Things like sentiment and tone, and whether it's a poem, and what underlying scientific truths are relevant to the piece, and things like that. Turning back one more time to our scorekeeping, GPT-3 includes 96 distinct layers, so the total number of key, query, and value parameters is multiplied by another 96, which brings the total sum to just under 58 billion distinct parameters devoted to all of the attention heads. That is a lot, to be sure, but it's only about a third of the 175 billion that are in the network in total. So even though attention gets all of the attention, the majority of parameters come from the blocks sitting in between these steps. In the next chapter, you and I will talk more about those other blocks, and also a lot more about the training process. A big part of the story for the success of the attention mechanism is not so much any specific kind of behavior that it enables, but the fact that it's extremely parallelizable, meaning that you can run a huge number of computations in a short time using GPUs. Given that one of the big lessons about deep learning in the last decade or two has been that scale alone seems to give huge qualitative improvements in model performance, there's a huge advantage to parallelizable architectures that let you do this. If you want to learn more about this stuff, I've left lots of links in the description. In particular, anything produced by Andrei Karpathy or Chris Olah tend to be pure gold. In this video, I wanted to just jump into attention in its current form, but if you're curious about more of the history for how we got here and how you might reinvent this idea for yourself, my friend Vivek just put up a couple videos giving a lot more of that motivation. Also, Britt Cruz from the channel The Art of the Problem has a really nice video about the history of large language models.
Hey, ever wondered what
Oh, what?
What does it mean for a computer to understand language?
Good question.
models.
I would like to watch this one day.
If you feed a large language model the phrase, Michael Jordan plays the sport of blank, and you have it predict predict what comes next, and it correctly predicts basketball, this would suggest that somewhere, inside its hundreds of billions of parameters, it's baked in knowledge about a specific person and his specific sport. And I think in general, anyone who's played around with one of these models has the clear sense that it's memorized tons and tons of facts. So a reasonable question you could ask is, how exactly does that work? And where do those facts live? Last December, a few researchers from Google DeepMind posted about work on this question, and they were using the specific example of matching athletes to their sports. And although a full mechanistic understanding of how facts are stored remains unsolved, they had some interesting partial results, including the very general high-level conclusion that the facts seem to live inside a specific part of these networks, known fancifully as the multi-layer perceptrons, or MLPs for short. In the last couple of chapters, you and I have been digging into the details behind transformers, the architecture underlying large language models, and also underlying a lot of other modern AI. In the most recent chapter, we were focusing on a piece called attention, and the next step for you and me is to dig into the details of what happens inside these multi-layer perceptrons, which make up the other big portion of the network. The computation here is actually relatively simple, especially when you compare it to attention. It boils down essentially to a pair of matrix multiplications with a simple something in between. However, interpreting what these computations are doing is exceedingly challenging. Our main goal here is to make it simple, especially when you compare it to attention. It boils down essentially to a pair of matrix multiplications with a simple something in between. However, interpreting what these computations are doing is exceedingly challenging. Our main goal here is to step through the computation.
So weird. But like, it's like, she must build something and this is to understand it, bro.
And make them memorable, but I'd like to do it in the context of showing a specific example of how one of these blocks could, at least in principle, store a concrete fact. Specifically, it'll be storing the fact that Michael Jordan plays basketball. I should mention the layout here is inspired by a conversation I had with one of those DeepMind researchers, Neil Nanda. For the most part, I will assume that you've either watched the last two chapters or otherwise you have a basic sense for what a transformer is, but refreshers never hurt, so here's the quick reminder of the overall flow. You and I have been studying a model that's trained to take in a piece of text and predict what comes next. That input text is first broken into a bunch of tokens, which means little chunks that are typically words or little pieces of words. And each token is associated with a high-dimensional vector, which is to say a long list of numbers. This sequence of vectors then repeatedly passes through two kinds of operation. Attention, which allows the vectors to pass information between one another, and then the multi-layer perceptrons, the thing that we're going to dig into today. And also there's a certain normalization step in between. After this sequence of vectors has flowed through many different iterations of both of these blocks, by the end, the hope is that each vector has soaked up enough information, both from the context, all of the other words in the input, and also from the general knowledge that was baked into the model weights through training, that it can be used to make a prediction of what token comes next. One of the key ideas that I want you to have in your mind is that all of these vectors live in a very high dimensional space, and when you think about that space, different directions can encode different kinds of meaning. So a very classic example that I like to refer back to is how if you look at the embedding of woman and subtract the embedding of man, and you take that little step and you add it to another masculine noun, something like uncle, you land somewhere very close to the corresponding feminine noun. In this sense, this particular direction encodes gender information. And the idea is that many other distinct directions in this super high dimensional space could correspond to other features that the model might want to represent. In a transformer, these vectors don't merely encode the meaning of a single word, though. As they flow through the network, they imbibe a much richer meaning based on all the context around them, and also based on the model's knowledge. Ultimately, each one needs to encode something far beyond the meaning of a single word, since it needs to be sufficient to predict what will come next. We've already seen how attention blocks let you incorporate context, but a majority of the model parameters actually live inside the MLP blocks, And one thought for what they might be doing is that they offer extra capacity to store facts. Like I said, the lesson here is going to center on the concrete toy example of how exactly it could store the fact that Michael Jordan plays basketball. Now, this toy example is going to require that you and I make a couple of assumptions about that high-dimensional space. First, we'll suppose that one of the directions represents the idea of a first name Michael, and then another nearly perpendicular direction represents the idea of the last name Jordan, and then yet a third direction will represent the idea of basketball. So specifically what I mean by this is if you look in the network and you pluck out one of the vectors being processed, if its dot product with this first name Michael direction is 1, that's what it would mean for the vector to be encoding the idea of a person with that first name. Otherwise, that dot product would be 0 or negative, meaning the vector doesn't really align with that direction. And for simplicity, let's completely ignore the very reasonable question of what it might mean if that dot product was bigger than 1. Similarly, its dot product with these other directions would tell you whether it represents the last name Jordan or basketball. So let's say a vector is meant to represent the full name, Michael Jordan. Then its dot product with both of these directions would have to be 1. Since the text Michael Jordan spans 2 different tokens, this would also mean we have to assume that an earlier attention block has successfully passed information to the second of these 2 vectors, so as to ensure that it can encode both names. With all of those as the assumptions, let's now dive into the meat of the lesson. What happens inside a multi-layer perceptron? You might think of this sequence of vectors flowing into the block, and remember, each vector was originally associated with one of the tokens from the input text. What's going to happen is that each individual vector from that sequence goes through a short series of operations, we'll unpack them in just a moment, and at the end, we'll get another vector with the same dimension. That other vector is going to get added to the original one that flowed in, and that sum is the result flowing out. This sequence of operations is something you apply to every vector in the sequence, associated with every token in the input, and it all happens in parallel. In particular, the vectors don't talk to each other in this step. They're all kind of doing their own thing. And for you and me, that actually makes it a lot simpler, because it means if we understand what happens to just one of the vectors through this block, we effectively understand what happens to all of them. When I say this block is going to encode the fact that Michael Jordan plays basketball, what I mean is that if a vector flows in that encodes first name Michael and last name Jordan, then this sequence of computations will produce something that includes that direction basketball, which is what we'll add on to the vector in that position. The first step of this process looks like multiplying that vector by a very big matrix. No surprises there, this is deep learning. And this matrix, like all of the other ones we've seen, is filled with model parameters that are learned from data, which you might think of as a bunch of knobs and dials that get tweaked and tuned to determine what the model behavior is. Now, one nice way to think about matrix multiplication is to imagine each row of that matrix as being its own vector, and taking a bunch of dot products between those rows and the vector being processed, which I'll label as E for embedding. For example, suppose that very first row happened to equal this first name Michael direction that we're presuming exists. That would mean that the first component in this output, this dot product right here, would be 1 if that vector encodes the first name Michael, and 0 or negative otherwise. Even more fun, take a moment to think about what it would mean if that first row was this first name Michael plus last name Jordan direction. And for simplicity, let me go ahead and write that down as M plus J. Then taking a dot product with this embedding E, things distribute really nicely, so it looks like M dot E plus J dot E. And notice how that means the ultimate value would be 2 if the vector encodes the full name, Michael Jordan, and otherwise it would be 1 or something smaller than 1. And that's just one row in this matrix. You might think of all of the other rows as in parallel asking some other kinds of questions, probing at some other sorts of features of the vector being processed. Very often this step also involves adding another vector to the output, which is full of model parameters learned from data. This other vector is known as the bias. For our example, I want you to imagine that the value of this bias in that very first component is -1. Meaning our final output looks like that relevant dot product, but -1. You might very reasonably ask why I would want you to assume that the model has learned this, and in a moment you'll see why it's very clean and nice if we have a value here which is positive if and only if our vector encodes the full name Michael Jordan, and otherwise it's 0 or negative. The total number of rows in this matrix, which is something like the number of questions being asked, in the case of GPT-3, whose numbers we've been following, is just under 50,000. In fact, it's exactly 4 times the number of dimensions in this embedding space. That's a design choice. You could make it more, you could make it less, but having a clean multiple tends to be friendly for hardware. Since this matrix full of weights maps us into a higher dimensional space, I'm going to give it the shorthand W up. I'll continue labeling the vector we're processing as E, and let's label this bias vector as B up and put that all back down in the diagram. At this point, a problem is that this operation is purely linear, but language is a very non-linear process. If the entry that we're measuring is high for Michael plus Jordan, it would also necessarily be somewhat triggered by Michael plus Phelps, and also Alexis plus Jordan, despite those being unrelated conceptually. What you really want is a simple yes or no for the full name. So the next step is to pass this large intermediate vector through a very simple non-linear function. A common choice is one that takes all of the negative values and maps them to 0, and leaves all of the positive values unchanged. And continuing with the deep learning tradition of overly fancy names, this very simple function is often called the rectified linear unit, or ReLU for short. Here's what the graph looks like. So taking our imagined example where this first entry of the intermediate vector is 1, if and only if the full name is Michael Jordan, and 0 or negative otherwise, after you pass it through the ReLU, you end up with a very clean value where all of the 0 and negative values just get clipped to 0. So this output would be 1 for the full name Michael Jordan and 0 otherwise. In other words, it very directly mimics the behavior of an AND gate. Often, models will use a slightly modified function that's called the JLU, which has the same basic shape, it's just a bit smoother. But for our purposes, it's a little bit cleaner if we only think about the ReLU. Also, when you hear people refer to the neurons of a transformer, they're talking about these values right here. Whenever you see that common neural network picture with a layer of dots and a bunch of lines connecting to the previous layer, which we had earlier in this series, that's typically meant to convey this combination of a linear step, a matrix multiplication, followed by some simple term-wise non-linear function like a ReLU. You would say that this neuron is active whenever this value is positive, and that it's inactive if that value is 0. The next step looks very similar to the first one. You multiply by a very large matrix and you add on a certain bias term. In this case, the number of dimensions in the output is back down to the size of that embedding space, so I'm going to go ahead and call this the down projection matrix. And this time, instead of thinking of things row by row, it's actually nicer to think of it column by column. You see, another way that you can hold matrix multiplication in your head is to imagine taking each column of the matrix and multiplying it by the corresponding term in the vector that it's processing, and adding together all of those rescaled columns. The reason it's nicer to think about this way is because here the columns have the same dimension as the embedding space, so we can think of them as directions in that space. For instance, we will imagine that the model has learned to make that first column into this basketball direction that we suppose exists. What that would mean is that when the relevant neuron in that first position is active, we'll be adding this column to the final result. But if that neuron was inactive, if that number was 0, then this would have no effect. And it doesn't just have to be basketball. The model could also bake into this column many other features that it wants to associate with something that has the full name Michael Jordan. And at the same time, all of the other columns in this matrix are telling you what will be added to the final result if the corresponding neuron is active. And if you have a bias in this case, it's something that you're just adding every single time, regardless of the neuron values. You might wonder what's that doing? As with all parameter-filled objects here, it's kind of hard to say exactly. Maybe there's some bookkeeping that the network needs to do, but you can feel free to ignore it for now. Making our notation a little more compact again, I'll call this big matrix W down, and similarly call that bias vector B down, and put that back into our diagram. Like I previewed earlier, what you do with this final result is add it to the vector that flowed into the block at that position, and that gets you this final result. So for example, if the vector flowing in encoded both first name Michael and last name Jordan, then because this sequence of operations will trigger that AND gate, it will add on the basketball direction, so what pops out will encode all of those together. And remember, this is a process happening to every one of those vectors in parallel. In particular, taking the GPT-3 numbers, it means that this block doesn't just have 50,000 neurons in it, it has 50,000 times the number of tokens in the input.
What the fuck?
So that is the entire operation. 2 matrix products, each with a bias added, and a simple clipping function in between. Any of you who watched the earlier videos of the series will recognize this structure as the most basic kind of neural network that we studied there. In that example, it was trained to recognize handwritten digits. Over here, in the context of a transformer for a large language model, this is one piece in a larger architecture, and any attempt to interpret what exactly it's doing is heavily intertwined with the idea of encoding information into vectors of a high-dimensional embedding space. That is the core lesson, but I do want to step back and reflect on 2 different things. The first of which is a kind of bookkeeping, and the second of which involves a very thought-provoking fact about higher dimensions that I actually didn't know until I dug into transformers. In the last 2 chapters, you and I started counting up the total number of parameters in GPT-3 and seeing exactly where they live, so let's quickly finish up the game here. I already mentioned how this up projection matrix has just under 50,000 rows, and that each row matches the size of the embedding space, which for GPT-3 is 12,288. Multiplying those together, it gives us 604 million parameters just for that matrix. And the down projection has the same number of parameters, just with a transposed shape. So together, they give about 1.2 billion parameters. The bias vector also accounts for a couple more parameters, but it's a trivial proportion of the total, so I'm not even going to show it. In GPT-3, this sequence of embedding vectors flows through not 1, but 96 distinct MLPs, so the total number of parameters devoted to all of these blocks adds up to about 116 billion. This is around 2/3 of the total parameters in the network, and when you add it to everything that we had before for the attention blocks, the embedding, and the unembedding, you do indeed get that grand total of 175 billion as advertised. It's probably worth mentioning there's another set of parameters associated with those normalization steps that this explanation has skipped over, but like the bias vector, they account for a very trivial proportion of the total. As to that second point of reflection, you might be wondering if this central toy example we've been spending so much time on reflects how facts are actually stored in real large language models. It is true that the rows of that first matrix can be thought of as directions in this embedding space, and that means the activation of each neuron tells you how much a given vector aligns with some specific direction. It's also true that the columns of that second matrix tell you what will be added to the result if that neuron is active. Both of those are just mathematical facts. However, the evidence does suggest that individual neurons very rarely represent a single clean feature like Michael Jordan. And there may actually be a very good reason this is the case, related to an idea floating around interpretability researchers these days known as superposition. This is a hypothesis that might help to explain both why the models are especially hard to interpret, and also why they scale surprisingly well. The basic idea is that if you have an n-dimensional space,
We don't even know why they scale that well, apart from the parallelism and oh my, why?
well, the basic idea is that if you have an n-dimensional space and you want to represent a bunch of different features using directions that are all perpendicular to one another in that space, that way if you add a component in one direction, it doesn't influence any of the other directions, then the maximum number of vectors you can fit is only n, the number of dimensions. To a mathematician, actually, this is the definition of dimension. But
Choose the largest each.
where it gets interesting is if you relax that constraint a little bit and you tolerate some noise. Say you allow those features to be represented by vectors that aren't exactly perpendicular, they're just nearly perpendicular, maybe between 89 and 91 degrees apart. If we were in 2 or 3 dimensions, this makes no difference. That gives you hardly any extra wiggle room to fit more vectors in, which makes it all the more counterintuitive that for higher dimensions, the answer changes dramatically. I can give you a really quick and dirty illustration of this using some scrappy Python. that's going to create a list of 100 dimensional vectors, each one initialized randomly, and this list is going to contain 10,000 distinct vectors, so 100 times as many vectors as there are dimensions. This plot right here shows the distribution of angles between pairs of these vectors. So because they started at random, those angles could be anything from 0 to 180 degrees. But you'll notice that already, even just for random vectors, there's this heavy bias for things to be closer to 90 degrees. Then what I'm going to do is run a certain optimization process that iteratively nudges all of these vectors so that they try to become more perpendicular to one another. After repeating this many different times, here's what the distribution of angles looks like. We have to actually zoom in on it here, because all of the possible angles between pairs of vectors sit inside this narrow range between 89 and 91 degrees. In general, a consequence of something known as the Johnson-Lindenstrauss lemma is that the number of vectors you can cram into a space that are nearly perpendicular like this grows exponentially with the number of dimensions. This is very significant for large language models, which might benefit from associating independent ideas with nearly perpendicular directions. It means that it's possible for it to store many, many more ideas than there are dimensions in the space that it's allotted. This might partially explain why model performance seems to scale so well with size. A space that has 10 times as many dimensions can store way, way more than 10 times as many independent ideas. And this is relevant not just to that embedding space where the vectors flowing through the model live, but also to that vector full of neurons in the middle of that multi-layer perceptron that we just studied. That is to say, at the sizes of GPT-3, it might not just be probing at 50,000 features, but if it instead leveraged this enormous added capacity by using nearly perpendicular directions of the space, it could be probing at many, many more features of the vector being processed. But if it was doing that, what it means is that individual features aren't going to be visible as a single neuron lighting up. It would have to look like some specific combination of neurons instead, a superposition. For any of you curious to learn more, a key relevant search term here is sparse autoencoder, which is a tool that some of the interpretability people use to try to extract what the true features are, even if they're very superimposed on all these neurons. I'll link to a couple really great Anthropic posts all about this. At this point, we haven't touched every detail of a transformer, but you and I have hit the most important points. The main thing that I want to cover in a next chapter is the training process. On the one hand, the short answer for how training works is that it's all backpropagation, and we covered backpropagation in a separate context with earlier chapters in the series. But there is more to discuss, like the specific cost function used for language models, the idea of fine-tuning using reinforcement learning with human feedback, and the notion of scaling laws. Quick note for the active followers among you, there are a number of non-machine learning related videos that I'm excited to sink my teeth into before I make that next chapter, so it might be a while, but I do promise it'll come in due time. So, if machine learning laws,
Yeah, similar. But damn, dude, crazy stuff. So, good average view duration for today. Now, I think I'll just don't know. Bhai, this is a bit scary, no? Because we literally don't understand anything of what's happening inside. And is this the first thing where we don't understand anything? Because, like, I don't know. I think the most complex thing I think that humans have ever built is probably internal combustion engine or the advanced forms of it, like jet engine or rocket engines and all of that. We know how that stuff works. Like, we know कि एक इंजेक्टर होता है, फिर उसमें से फ्यूल जाता है and then spark होता है, blah blah blah. This is weird, bro. Like, we just don't know. Like, what do you mean we just don't know? Shouldn't be like no, because like we're making it. But weird. Anyways, so tomorrow we'll go through Karpati. Not the whole thing, of course, because the whole thing is like 20 hours long. I don't know. But yeah, we'll study Karpati and understand background and all. And also we need to we need to do all these things. I'll do these offline only. I won't stream it. But I'll skip out. We can do this. We did NLP basics with tokenization and embeds and decoders, or we didn't do decoders. We can did NLP basics. Also did transform architecture. It went a bit too deep for it, I feel. But yeah, we did day 2 also. Nice. And then what? Then tomorrow Karpati and setting up of the environment and whatever, and then we'll do some basic stuff. Okay, on that note, good night, sweet dreams. I don't know who is watching, but I need to be polite, yaar, क्योंकि आगे जाके what if someone is watching, someone looks back, what if I bring a Nobel or something, and someone is like, oh, this is where it all started. Okay, on that note, good night. Love you.